experimental measurements of enthalpy. So we want to see how we can determine enthalpy changes of various chemical reactions by carrying out experiments. So remember, we normally apply the formula delta H, or enthalpy change, is equals to M times C times delta T. M stands for mass of solution, C stands for specific heat capacity, which is normally a constant, that is 4.2. It can be in kilojoules per kilogram per Kelvin, or it can be given in terms of joules per gram per Kelvin. Then delta T in that expression stands for temperature change. How do you get temperature change? For any given reaction, whether exothermic or endothermic reaction, you take the final temperature minus the initial temperature. So if there is a temperature increase, that one means it is an exothermic reaction. If there is a temperature decrease, that means it is an endothermic reaction. So then, we want to look at the first example. Example 1. This experiment is a neutralization reaction where we are combining an acid and a base to form a salt and water. So we have been given the volume 50 cubic centimeters of 1 molar HCl reacting with 50 cubic centimeters of 1 molar sodium hydroxide. These are equimolar solutions. So the initial temperature of each of these solutions is 18 degrees Celsius. Then the temperature rise is 24 degrees Celsius. This is the highest temperature. So if you want to get the temperature increase, we take 24 minus 18, which will give us a 6 degrees Celsius. So remember, this one is an exothermic reaction. So applying the formula, enthalpy change or heat energy change is equals to mass times specific heat capacity times temperature change. So in this case, our mass of solution, given that we are mixing two liquids, that is HCl and sodium hydroxide, then you get the sum of the two. 50 plus 50, you get 100 cubic centimeters. Then remember, you need to convert it into grams. So use the density of water, which is 1 gram per cubic centimeters. So if 1 cubic centimeters is 1 gram, what about 100 cubic centimeters? This one will give us 100 grams. So we take 100 grams times 4.2 joules per gram per Kelvin times temperature change, which will be 6 Kelvin. So remember, we normally work with kelvins. So when you get the difference, you give your value in terms of Kelvin. So when you multiply here, you will get 2,520 joules of heat. Then now you proceed and get the number of moles of sodium hydroxide or the number of moles of HCl. Remember, the mole ratio is 1:1. So when you react these two reactants, you will form salt and water. So you'll form 1 mole of water. So the mole ratio of HCl to sodium hydroxide to water is 1:1:1. So you can work either the moles of HCl or the moles of sodium hydroxide. So once we tabulate here, remember we can use sodium hydroxide. We have 50 cubic centimeters. Then the solution is 1 molar. It means 1000 cubic centimeters contains 1 mole of sodium hydroxide. What about 50 cubic centimeters? This one will give us 0.05 moles of sodium hydroxide, which is equivalent to the number of moles of water formed. So that means if 0.05 moles of water are formed, 2,520 joules of heat is evolved. What about 1 mole? So that means you take 2,520 divided by 0.05, which will give us 50,400 joules per mole of heat, which can be converted into kilojoules per mole by dividing by, you divide by 1,000. So when you divide by 1,000, you get 50.4 kilojoules per mole. So we put this negative value here because this reaction is an exothermic reaction. So the two main ways of investigating enthalpy changes are: one, mixing substances in an insulated container. Insulated container is meant to conserve heat so that there is no heat loss during the reaction to minimize errors. Then part B, using a calorimeter in a combustion experiment. So I believe you know what a calorimeter is. It's normally used to determine enthalpy changes. So the likely errors that are incurred in the experiment one is that there is an assumption that the volume of water used in the calculation is the same as the volume of the solution used in the reaction. So sometimes we normally use mass of solution, which is water. So they assume the volume of water is the same as the volume of the solution used in the reaction. Then number two, assuming that the specific heat capacity of the solution is the same as that of water. So remember I told you that 4.2 is normally the specific heat capacity of water, which is commonly used in carrying out calculations to determine enthalpy change. Then remember there is always some heat loss to the surrounding. So some heat can be lost to the surrounding, which can result to incurring an error between the theoretical value and the actual value. Then experiment 2, I want to see how we can use a calorimeter to determine enthalpy of combustion for a given reaction. So a calorimeter could be used to measure enthalpies of combustion. A typical proof of this is outlined below. So this is a procedure. So you measure 100 cubic centimeters of water, then put it in a calorimeter, which is basically a metal can. So the liquid to be investigated is placed in a spirit lamp. The spirit lamp is weighed. So here we normally use either any flammable substance. It can be ethanol or it can be methanol as per this experiment. So the temperature of water is noted. So you use a thermometer to measure the initial temperature of water as per this diagram here. So the apparatus is set up as shown below. So you first of all take the initial mass of methylated spirit plus the lamp. This one will give us the initial mass. Then at the end of the experiment, you also weigh the remaining methylated spirit plus the lamp and record the mass. Then also you must record the final temperature of water. So after a temperature rise of around 20 degrees Celsius, the flame is extinguished. So that means you monitor the experiment so that once you get that temperature rise of 20 degrees Celsius, you put off the lamp. So the exact temperature is noted. The burner is weighed to find out how much liquid has been burned. So remember you must follow the experiment carefully so that you get accurate measurements. So this table shows the results at the end of the experiment. So you have the liquid, which is an investigating substance. Then you have ethanol, which is the one which burns. So the initial mass of the burner at the start of the experiment is 115.78 grams. Then mass of the burner at the end of the experiment is 115.59 grams. So that means the difference between the two will give us the mass of the ethanol which will have been burnt during the experiment. Then the initial temperature of water is 21 degrees Celsius and the final temperature is 29 degrees Celsius. So these two values will give us a temperature difference during the reaction. Then you come and substitute in that formula. So enthalpy change is equals to, so you take M times C times temperature change. So our M, we use the mass of the solution. So remember we use the mass of the solution, not the mass of the fuel that burned, mass of water. So maybe you can just go back and look at that diagram. So this is our water. So you take the initial and the final temperature of water. So that means the volume of water used was 100 cubic centimeters. So you take 100 cubic centimeters, you multiply by 1 gram per cubic centimeters to convert that volume to grams. So we shall get 100 grams times 4.2 joules per gram per Kelvin times the temperature difference, which is 8 degrees Celsius. So 8 degrees Celsius, but we give our value in terms of Kelvin so that the units are uniform. So this one we multiply by 8 Kelvin. So if you carry out computation, you will get 3,360 joules of heat. Then the mass of ethanol burnt, when you get the difference, it will give us 0.19 grams. So you convert that mass into moles. So to get moles, we normally take mass all over molar mass. So the molar mass of ethanol is 44 grams. So remember, one atom of carbon is normally has a mass of 12. Then one atom of hydrogen has a mass of 1 gram. And one atom of oxygen has a mass of 16. So when you get the sum of the masses of those atoms in this molecule, it will come to 44 grams. So when you convert that mass into moles, we shall get 0.0043 moles. Then now we say that if 0.0043 moles evolves this amount of heat, what about 1 mole? So we take 1 times this value divided by the number of moles, which will eventually give us this amount of heat in joules per mole, which is equivalent to 781.4 kilojoules per mole. So I think this calculation is straightforward. Remember, we use mass of water, which is 100 grams, then specific heat capacity 4.2 joules per gram per Kelvin, then temperature change. Remember, there's a temperature rise. This one is exothermic reaction. That's why you must put this negative value here. So it is negative 781 kilojoules per mole. So now, as students, you'll have to attempt this question. The enthalpies of combustion of ethane, hydrogen, and carbon are given here. Find the enthalpy of formation of ethane. So you'll have to attempt that question in groups and see how you can work it out. So now I want to move forward and look at enthalpy changes in solutions, where basically we are going to look at what happens or the various enthalpy changes when you dissolve ionic compounds in water. So basically we are going to look at some of the examples of ionic compounds. Then we are also going to define some of the terminologies which are used under enthalpy changes in solutions. So the first one, we look at standard enthalpy change of solution. What is the meaning of standard enthalpy change of solution? So it is normally denoted by that symbol, delta H naught. Naught means that enthalpy change has been determined under standard conditions of temperature and pressure. So standard enthalpy change of solution is the enthalpy change when 1 mole of an ionic compound or ionic compounds is dissolved in water to form an infinitely dilute solution under standard conditions. So when you dissolve 1 mole of magnesium chloride, a certain amount of heat will be involved. So standard enthalpy change of solution can be exothermic or endothermic. So when you dissolve some substances, heat is normally evolved, like sodium hydroxide is an example of substance which can evolve heat. So some of ionic compounds can also evolve heat, others involves absorption of heat from the surrounding. Then the second terminology, standard enthalpy change of hydration. What does it mean? Is the enthalpy change when 1 mole of gaseous ions dissolves in water to form hydrated ions of an infinitely dilute solution under standard conditions. So when gaseous ions of ionic compounds get solvated with water, heat is normally evolved. So that kind of energy change is called enthalpy change of hydration. So you have an example of a calcium ion in gaseous states. So when it becomes solvated or surrounded with water molecules, it will change from gaseous state to aqueous state. So the amount of heat given out is quantified in terms of enthalpy change. So that is enthalpy change of hydration. So standard enthalpy change of hydration is always exothermic, meaning that heat is usually evolved or released to the surrounding. So this bond is called the ion table bond. So remember, we have some factors which determines the magnitude of hydration during the reaction. So the first factor is the size of the ion. Then the second factor is the charge on the ion. So these two factors usually affect the amount of hydration energy or the enthalpy change during a solvation of gaseous ions of ionic compounds. So how does the size of the ion affect hydration energy? The larger the size of the ion, the lower the hydration enthalpy. For example, if you look at hydration enthalpy of group 2 ions, decreases down the group. So the larger the size of the ion, the lower the hydration energy. But if the size of the ion is small, it means the hydration energy will be more. Then in terms of the charge on the ion, the higher the charge of the ion, the higher the hydration energy. For example, if you compare group 2 ions and group 1 ions, group 2 ions have a charge of positive 2, while group 1 ions have a charge of positive 1. So that means group 2 ions have higher hydration energy. Like if you compare aluminium ions and sodium ions, aluminium ions have a charge of positive 3 and sodium ions have a charge of positive 1. So definitely aluminium ions, which have a higher charge, will have higher hydration energy. So now I want to look at the process of dissolving ionic compounds. Remember, as I told you earlier on, we have three types of enthalpy changes which are involved. We have enthalpy change of solution, enthalpy change of hydration, and lattice energy. So now, a solid ionic lattice is first broken down to form gaseous ions, and lattice energy is usually absorbed. Remember, during breaking of the bonds, it involves absorption of heat. It is an endothermic process. So that amount of enthalpy change which is involved during breaking of the bonds between ions in an ionic compound is called lattice energy. Then the gaseous ions are then solvated with the water molecules. They are surrounded with water molecules to form new bonds. So once they become surrounded with water molecules, hydration energy is normally experienced. So that enthalpy change is called enthalpy of hydration. Then when you dissolve an ionic compound in water to form a solution directly, so that direct link between ionic compound and aqueous ions is called enthalpy of solution. So remember, you covered that one in high school under energy changes. So now I want again to repeat by defining these terminologies. Enthalpy change of hydration. So what is enthalpy change of hydration? This is the enthalpy change when 1 mole of a gaseous ion dissolves in water to give an infinitely dilute solution. Then enthalpy change of solution. This is the enthalpy change when 1 mole of a substance dissolves in a solvent to give an infinitely dilute solution. So you can talk about solvent or water. Then, what is lattice energy? So we want to also define the term lattice energy. So if a pair of oppositely charged gaseous ions are placed together, they will attract each other. The enthalpy change involved is lattice enthalpy. So now we move forward, and before that we need to define what is lattice energy. So lattice energy is the enthalpy change that occurs when 1 mole of ionic compounds are formed from its elements in gaseous state in standard a form is the enthalpy change that occurs when 1 mole of an ionic compound is formed from the gaseous ions of its elements in standard states. That is called a lattice energy. So you will make further reference so that you are able to get that information. So now I want to look at that example. Study the information given below and answer the questions that follow. So you have been given a hydration energy of X ion to be that. You have been given hydration energy of Y ion to be that. Then lattice energy of XY2 to be that. So remember, this one is an ionic compound. XY2 is just the same as like calcium chloride. Calcium chloride is an ionic compound, so it resembles this kind of formula. So X can stand for calcium, then Y can stand for chlorine, or X can stand for magnesium and Y can stand for chlorine. So magnesium chloride is an ionic compound, so just the same as that. So X and Y are not the actual symbols of elements, but they have just been used to represent a certain compound. So they are saying determine the heat evolved when 31.8 grams of XY2 is dissolved in water to give an infinitely dilute solution. So they have given us the RAM of Z to be 88, that is the molar mass of that element, and Y is 35.5. So when you get the sum of the mass of X and Y, it will give us the molar mass of that ionic compound. So first of all, I want us to look at this diagram to see how that compound can dissolve in water to give us various type of enthalpy changes. So if you look at that particular diagram, XY2 is our ionic compound. So when you dissolve it in water, first of all, these ions will dissociate and exist in gaseous state. So for X, remember it has a positive charge of 2. Because of that valence under Y, it means X has a valence of 2. That's why it has 2 positive here. So it is 1 mole of that ion plus, so remember you have 2 moles of Y, and Y has a valence of 1 from this formula. It's a negative. Remember it's an ion. But we have 2 of them, so we have 2 moles of Y ions, as you can see in that formula. So the first enthalpy change is lattice energy. Remember, heat is absorbed during breaking of the bonds. So that's why it is positive, 2112 kilojoules per mole. Then an ionic compound can change into, it can dissolve and form ions directly, as you can see. So this arrow from the reactants to the final product is enthalpy change of solution. So again we form 1 mole of X ion and 2 moles of Y ions. Remember, use this formula to balance the ions, both in the intermediate and in the final product. If X here is 1, it must be here 1. If there are 2 Y, you must put 2, the coefficient before Y ions. The same applies to the intermediate products, as you can see here. Then remember, when you dissolve 1 mole of X ionic compound, this amount of heat is given out. I think it is in the question. Then, when these gaseous ions become surrounded with water or they are solvated with water, hydration energy is obtained. But when 1 mole of X ion is solvated with water, the amount of heat given out is negative 364 kilojoules per mole. It is 1480 kilojoules per mole, I mean. So that one is for X ion. Then for Y ion, 1 mole is negative, it is 364 kilojoules per mole. But because there are 2 moles here, we multiply 2 times 364, as you can see here. So we get negative 728. Now they are given negative sign because during bond formation, heat must be given out or it is evolved. So when you get the sum of the two, the enthalpy of X ion plus the enthalpy of 2 moles of Y ion. So 1480 plus 728, it will give us 2208 kilojoules per mole. So this one is now the sum of hydrogen energies for both X and Y. So it is here along this arrow here. So that means now to get the enthalpy of solution is equals to lattice energy plus hydration energy. So it means if you want to move from these reactants to products direct, we can move from here and take this, we follow Hess law, we can move this direction, then we come downward like that. So from our calculations, you can see a heat of enthalpy of solution is equals to 2112 plus, in brackets, minus 2208. Remember, this one is obtained from this one now. You take 1480 plus 2 times 364, as you can see in that particular calculations. So when it is worked out very well, you can see the answer becomes a negative 96 kilojoules per mole. That one is the enthalpy of solution here, negative 96 kilojoules per mole. So that means when you dissolve 1 mole of that ionic compound in water, this amount of heat is given out. But now, remember from the question, they dissolved that 1.8 grams. So they want the amount of heat which is given out when that 1.8 grams were dissolved. So that means you proceed and get the molar mass of that compound. So the molar mass, you can see they have worked out to be 159. So we say if 159 grams evolves 96 kilojoules of heat, what about that 1.8 grams? So when it is calculated very well, you can see the answer becomes 19.2 kilojoules of heat. So the final answer becomes negative 19.2 kilojoules of heat. So that is the expected answer. So you can go slowly through that example. Once more, you can go through slowly by slowly so that you are able to understand how we worked out that question. So now we move next and look at, so that is how it was worked out. You can see how the molar mass was obtained. So if that mass evolves that amount of heat, what about that 1.8 grams? So I think you can be able to see very well. Good. So now next we want to move forward and look at Born-Haber cycle. Born-Haber cycle.